traveling west at 50 miles per hour, and car B is traveling north at 60 miles per hour. What should I do? Draw a picture. Okay, so we have car A is going west, car B is going north. Both are headed for the intersection of the two roads. So they didn't start at the same point, but they are going to meet here. So we have car A, let's say car A starts here, and it's going this way. And car B started down here, it's going north, and they are going to head for the intersection. So they are going to meet up. At what rate are the cars approaching each other when car A is 0.3 miles and car B is 0.4 miles from the intersection? All right, we need some labels in here. So I'm just going to call this side A, since that's where car A is traveling, and this is side B. And I'll just call the distance between them C. Are any of those three things constant? No, they're all changing because both cars are moving, so the distance between them is changing. All right, miles per hour, what is that? It's speed, which means it is the derivative. So my dA dt is 50. Car B, so dB dt, is traveling at 60. We want to know how fast they are approaching each other. So we're looking for the speed this third side is changing. So dC dt is the thing we are searching for. We know car A is 0.3 miles from the intersection, so side A is 0.3, side B is 0.4. Did I give you side C at that point? No. Could we find side C at that instance? How? Okay. So we know A squared plus B squared would equal C squared. So at that particular instant, side C is 0.5. We already said we're doing Pythagorean theorem. If you had any constants, you would plug them in now, but we don't. Everything's changing in this problem. So what do I need to do? Derivative. What's the derivative of A squared? 2A plus derivative of B squared, 2B dB dt equals derivative of C squared would be 2C dC dt. And now we plug in everything. 0.3, dA dt is 50. B is 0.4, dB dt is 60, C is 0.5, we do not know dC. T is 78. What would my units be? C would be a distance of miles per, T was time, so hour. So they're approaching each other at 78 miles per hour. any questions on? So I would like for you to read the next problem and see if you can set up, draw a picture, label, see how far you can get with it. So we have a girl is flying a kite on a string. So the kite, string, look like that. The kite is 120 feet above the ground, and the wind is blowing it horizontally away from her at 6 feet per second. So it's traveling away. I know the height off the ground is 120. Is that changing or constant? Constant. So I can go ahead and label that as 120. Anything that's changing should be variables. If the kite is being blown away from her, is this distance the same or changing? Changing. So that should be a variable. So whatever you want to call it. Okay. At what rate must she let out the stream when 130 feet of string has been let out? We know it's being blown away horizontally. So is this side the same or changing? Changing. So that needs to be a variable. Do I need to flip my x and y to match what you guys did, or do you care? So here's what we have. One side's constant, so we went ahead and labeled it with a number. The other sides are changing, so they get variables. So now we need to figure out what all the numbers represent. It's blowing horizontally away at 6 feet per second. So which variable represents my horizontal? The y. And since it's feet per second, that is the dy dt. At what rate must she let out the string? So the string is side x. Since I want an x, or a rate, I'm looking for dx dt. So that's what we're trying to find. When 130 feet of string, so x is my string, so we're looking at the instant when the x is 130. Questions there? What next? Find y at this instant. So we know y is changing, but it is a triangle. So y squared plus 120 squared would equal x squared, so 130 squared. So at that instant, my y is 50. Alright, now I need to get my dx dt into my problem. So what do? We need the derivative. We're going back to the same formula. The y squared plus 120 squared equals x squared, but x and y have to be variables because they change. Derivative of y squared would be 2y dy dt. 120 squared, that's just a constant, so the derivative would be 0, so that goes away. Derivative of x squared would be 2x dx dt. units be? X was a distance, so that would be in feet. In this problem, time was measured in seconds. So 30 over 39 feet per second. Sorry, 30 over 13 feet per second. Right, are you guys getting a feel for which numbers can be plugged in at the beginning and which ones we have to wait until after the derivative? Anything that never changes, you plug in at the beginning. Any quantity that's changing, we have to wait until after the derivative. Plug in. Let's do one more problem for today. That'll be our stopping point. So a water tank has the shape of an inverted circular cone with base radius 2 meters and height 4 meters. What does that mean? What's an inverted circular cone? Like an ice cream, like a waffle cone. You know, so inverted just means it's upside down. It's a cone. The base is circular. So we have the base radius is 2 meters. So that means if I'm looking here, this distance is 2, and the total height of this cone is 4. Do a quick check. Are all my units meters in this problem? Okay, so we're okay. If I gave you something in meters and something in centimeters, we'd have to convert first. But all of our units match, so we're good. Water is being pumped into the tank at a rate of 2 cubic meters per minute. Find out the rate at which the water level is rising at the instant when the water is 3 meters deep. So what's happening is we are filling this cone. Okay, so we've got water coming in, and as that happens, the water level is rising. Is the height of this water constant or changing? Changing. So this is my height, and I know at the one particular instant we need, the height is 3. We're looking for the rate the water level is rising. So a rate is a derivative, so we are looking for dH dt. What would 2 cubic meters per minute represent? The volume. Cubic is volume, and since it's per, that's dV dt. Volume of a cone is 1/3 pi r squared h. Volume of a cylinder is pi r squared h. A cone is 1/3 of it. Okay, so here's the problem. If I do my derivative right now, I will end up with a dV dt, a dr dt, and a dH dt, right? I need to find dH dt, and I have dV dt, but have I given you anything about the radius? No. So really, if I'm going to be able to find dH dt, I have to get rid of that radius before I do the derivative. Okay, so we need to go back and look at the other information again. I really need to be able to change r to something else. And I don't know the number, and it's changing anyway. But what we do know is that in this whole cone, the radius is 2 and the height is 4. Okay, and if I took a similar triangle, this is my height, and that's my radius. Good morning. Good. Alright, So what could we do with similar triangles? Okay, we could set up a proportion, couldn't we? Do you remember with similar triangles? Like you could say R over H would be equal to 2 over 4. We're trying to figure out what R is, so if you multiply over H, R is 1/2 H. So I didn't find the number for the radius, but I found a formula. The radius is always going to be half the height, no matter where we're at in this cone. So, because I don't want the radius when I do my derivative, I'm going to change the radius to 1/2 H. And I'd like to clean this up as much as I can before I did the derivative. So 1/3 times pi would be pi over 3. 1/2 squared is 1/4. So my volume is pi over 12 H cubed. So now, what can we do? Derivative of v would be dv dt. Okay, 3 comes down. H squared dh dt. So we can plug in what we know. dv dt was 2. 3 pi over 12, that reduces to pi over 4, which is 3 squared. We don't know dh dt. So we get 8 over 9 pi. Units. The height is measured in meters per time in this problem was. So the whole reason we had to do this extra work before the derivative was we had a radius, but I did not give you a dr dt. So we had to get rid of the radius before doing the derivative. That one was definitely a little more challenging. Questions there? I told you that was the last one, but there's really one more that I kind of wanted to do. Why don't you take a few minutes? I want you to do a few homework problems, and I might do one more example before you do problem 13. Okay. So the homework, the next chunk, 9, 11, and 13. I want you to do 9 and 11. Read 13. We may need to do something kind of similar to that before you actually solve that problem.